I'm Vikram. I'm a software engineer in the Angular team at Google, and welcome to my talk on how we use Node to help propel Angular. The talk is also about how we manage to run Node inside Google. So just a short introduction to Angular. How many of you are aware of Angular or have used Angular before? Okay, I'll skip this slide. It's a framework for building large-scale web applications, so it's good. Late last year, we had a customer come to us with a problem, essentially. The customer was Google Shopping Express, so they are the same-day delivery service from Google. So they are an Angular application, and they were seeing an increase in like 3G mobile traffic to their site because of various campaigns and promotions that they have been running. And so what this led to was that they were seeing increase in the load times for the site, as seen as an average of all load times across devices. They wanted to essentially have a goal for reducing their time to first paint, which is or meaningful paint, where their user sees important meaningful data on their website on 3G on a low-end device to be less than 3 seconds. We have a project called Angular Universal. Again, how many of you are aware of Angular Universal? Few of you, like 6 of you. So Angular Universal is essentially a project that lets you run Angular on a Node.js server so that you can do server-side rendering of Angular apps. So how does it help with the problem? So essentially consider like a mobile browser. So mobile browser is essentially requesting for a particular route in your website. And at that point, we run your Angular application on Node.js as a universal app. And instead of sending just an empty HTML and JavaScript to boot on the client, we do the initial rendering on the server and send back a fully rendered HTML page of the route that you requested, and then send in the JavaScript. So on a low-power device, on a 3G network or a slow network, the user is able to see the content much faster than if we just sent a bunch of JavaScript. Right? So we decided that we'll use this to help Shopping Express. So the problem then comes like, how do you run Node.js in Google? The standard Google server languages are essentially C++, Java, and Go. And what makes them standard is they are hooked into the Google infrastructure that lets them do like RPC, and that infrastructure is called Stubby, logging, monitoring, load balancing, and security and stuff like that. So Node as a platform is not supported to do any of these Google-specific things. So our first challenge was to even get this off the ground, right? So just to give some background of how web applications are built inside Google, so you can think of like a loose microservices architecture with different services talking to each other using a low latency RPC mechanism called Stubby. So in case of a front-end server, it might be querying different back-end services using Stubby, and this way you can have different aspects of your applications handled by different microservices. So in our case, we wanted to essentially create server-side rendering service based on Node.js. So you have the Java front-end server, which is the standard front-end server used inside Google. We still maintain that. And we created a new Node.js render service. And for Shopping Express, we put the Shopping Express app into it. And whenever a request came to the Java front-end server, it would do all the API calls to fetch the data to render that page, and then send that data over Stubby to the Node service asking for rendering to be performed. And then Node.js service essentially runs Angular Universal and renders the HTML and sends it back to the front-end server, which then sends it back to the client. So this is like the very initial architecture we had. And we wanted to just see like what is the overhead of having this Node server run as a separate service on a separate physical machine from your front-end server, right? Actually, it turned out to be not that bad. The rendering itself was taking quite a bit of time. It was like 150 milliseconds, which was still okay considering the 3-second target we had for the end-to-end latency. And the Stubby overhead itself was in microseconds. So it didn't really matter that we were running in a separate physical machine, right? So we had this initial architecture, and the next thing we wanted to look at was how to harden this service to bring it to like Google standard security, right? So for this, we took an approach where we built different layers of defense. And at the core is Angular itself and TypeScript. Angular provides services to essentially sanitize your strings before they are rendered to your HTML. And there's a thing called DOM sanitizer, which is aware of the context in which you are trying to do the interpolation of some string and can apply the right kind of sanitizer. So this essentially allows us to prevent like cross-site scripting attacks in the client. And as it so happens, we can use the same thing to now prevent cross-site scripting when we are doing the server-side rendering. So it works the same way. On top of that, we did this other thing of banning the bypass security API. So Angular allows you to bypass the sanitizer if you're really sure you know what you're doing, but inside Google we said, no, we are not going to let you do that. So essentially to have like an extra layer of security. So the next layer is what we call the restricted node. We decided not to run vanilla Node.js, but to build our own version of Node where we could disable eval and we could whitelist the Node modules that can be loaded during build time. So during build time, we build a hash of all the files or modules that can be loaded. And when you have a require statement, it would match the path by the hash, and if it didn't match the hash, it would fail. So this was actually a system built by another team inside Google who had built this restricted node for experimentation purposes, which we were able to reuse for our purposes. So the last layer is actually like a catch-all. We then took this restricted node and ran inside OS level sandbox so that we can actually control what system calls our node binary could make. This was required by the security team because V8 or Node is not a system that is completely security reviewed, and we are just starting to use this in production. So this provides extra layer of guarantee such that if tomorrow there is some vulnerability found in Node, it gives us the time to patch it and release it without having to bring the whole system up. Right? So the one thing we did was actually at the OS sandbox level lock down the system, the Node.js process so much that actually it didn't have any like network support. So that again, if the service was compromised in some way, it could not make any network calls there. So we felt better like if we could sandbox it to that level. So to add back the network support, essentially we added a Go server that can handle all the networking for this render service. and would spawn the sandbox node child process and would talk to the child process only through pipes, which we had whitelisted in our sandbox. So this really provided like a watertight compartment, and we could control the security context in which this thing runs. And so the second iteration of our architecture was remove running Node directly, but have the sandbox node running inside the Go wrapper, right? And the other nice thing at this point was, since Go is one of the supported languages in Google, we got things like monitoring and logging for free. And we could have the Go process monitor the actions that were performed by Node and log them to our logging system so that we could track in a fine-grained manner, like what part of the system is taking what time, right? So we went back and tried to measure the overhead of this new system. So still had the 150 millisecond and few milliseconds from Stubby. At this point, essentially the security sandbox and talking to it over pipe was adding like 10 milliseconds, right? So we still think that it isn't too much compared to the rendering, and given the benefit of added security, we think it's worth having this over it. So at this point, we thought we had everything ready, go to production. We had done some simple stress testing, but we still knew that we had to address scalability better. So going back to the overhead slide, we did some rough calculations. So just the rendering service plus the security sandboxes takes about 160 milliseconds. So what that meant is, per instance, the number of renders that you could do is 1000 divided by 160 is like 6.25, right? This is not a great number compared to the traffic that you can imagine something like Google Shopping Express would have. So we said that's fine. We'll just add more instances of the rendering process, right? So even though in the previous diagrams I had showed the Java server directly talking to the Go node service, in reality what we have is, since the render process its own microservice, it's behind a load balancer, we have configuration to control how to scale the render service separately from the Java frontend, right? So even though the Go service, Go and Node render would be slow, our initial design was we would just spawn a lot of those instances, right? So having that, we did something called the dark launch. So what this meant is essentially we deployed this thing to production, like actual production environment. And whenever a request came, and it still did the query to the backends and send the request to the Go process, but at the same time it would just respond. The Java server would behave as if server-side rendering wasn't turned on, right? And the Node renderer would still do the server-side rendering and return back the result, but the result would just be ignored. So this provided us like a good way to do, like even though we had done stress testing in like a limited environment, this let us test it out in a real production environment, but actually not disrupt the production setup, right? And we got the initial results, and what we saw was like high latency all over the place. So we started looking at what was happening, and one thing that was happening a lot more than we expected was each instance getting a lot of concurrent requests. So just looking at our current setup, if you had two requests come in at the same time, since Node is a single-threaded process, and we didn't do anything to do more than that, the first request would be taken by the Node process, and it would take 150 milliseconds, while the second request is still waiting. And once the first request is done, the second request is picked up, and it would take another 150 milliseconds to do its job. So we would essentially, we are adding up the latency with the number of concurrent requests, etc. This was happening in like 2 cases when there was a spike in traffic, where the number of instances wasn't adjusted fast enough. And the second was the Java stubby client was actually doing like an optimization where it would batch few calls together and send it to a single instance. Even though there's a load balancer, it would send like a couple of requests together to the same node instance. So, and we were in no position to handle that. So just to step back, we essentially looked at like the scaling systems available inside Google. So, and we found that the configuration allowed us to do 2 separate types of scaling. One is scaling horizontally, where you could just increase the number of instances. And this is what we were essentially depending upon, and we thought we would be good. But the other kind of scaling available was increasing the number of cores or memory available to a single instance. And since we are still single-threaded, even though the system would give us more cores or memory, we weren't in a position to make use of it. So at this point, we essentially looked at how to make use of local cores if more is available. So we did the simplest thing of essentially just spawning a lot of node processes from the same renderer process. So we also found that Go provided like good primitives for us to maintain a pool of resources and be able to round robin through each one of them. So with this, we were able to scale vertically, make use of the resources better, and our latencies were back to what we expected them to be. So where does this put us? So the current status, we have now a way to run Node.js in production inside Google that is more closely aligned with Google infrastructure thanks to the Go wrapper that's security reviewed and scalable because we were able to better understand and make use of the scaling system inside Google. Shopping plus SSR is going to release anytime this week. And so we just ran some very initial experiments on a system even before production. The first meaningful paint time is down to 1.6 seconds, which was below our target of 3 seconds, down from 5.1 seconds. So we think this is a good improvement and forms like the base on which we can do further optimizations. So just to give an idea of what this looks for a user. So the left-hand side is essentially the server-side rendered version, and the right-hand side is just the client-side rendered version. Oops. All right. So this is again on a simulated slow 3G connection and with a CPU throttling turned off. As you can see on the left-hand side, the server-side rendered version shows like important data much quicker than the client-side rendered version, and you could almost browse through what the product page is saying even before the full page loads. So this is the real advantage of server-side rendering, and we are now able to deliver it to Google Teams also. So to summarize and create one slide with lots of words in it. So the things we did was like run Node.js as a separate service. So we initially thought this might be a problem, but at the end it didn't turn out to be much of a problem. We just use low latency RPC to talk to it, and you're fine. And having a separate service actually lets you scale better horizontally and separately from your front-end server, right? So compared to embedding, like doing things like embedding your Node.js into a Java server, I'd say just keep it as a separate instance and you are much better off. Secure service, this is true, especially if it's not managed for you. We went all the way through and locked it down as much as possible, so you have the options of doing nothing or make your node process talk through only a pipe and disable everything. Scalability, again, so we essentially found like server-side rendering is, at the end of the day, very CPU bound, which is very different from what Node.js loads with like more IO bound loads are. This meant we had to scale differently. I'd say in your case, specific case, understand your scaling options. And what I described was probably peculiar to Google, but I think it'd be better for you to understand your scaling options and build a solution that can make use of your infrastructure better. So that's the end of my talk. So you can check out like the Angular Universal Guide, where we talk about how to set up and convert like a client-side Angular application to run on the server using Node.js. And my slides are up there, and coming soon, we'll have the code for the Go server and how we did the pooling. And Stubby is available as something known as gRPC outside, so we'll have a gRPC version of all the rendering cells. Thank you. All right.